Okay, looks like the doors are shut, so we can make a start. Good afternoon, everyone. I hope everyone's having a good time at AU so far. Not long till the finish line. Everyone's looking forward to the party tonight. Awesome. All right, so welcome to Civil 3D and Dynamo, Dynamic Culvert Design and Analysis. My name is Andrew Milford. I'm an implementation consultant working for Autodesk. I've been with Autodesk for about the last 5 years, but my background extends way into civil engineering for nearly 25 years. So I've worked for companies like AECOM, Arcadis, Jacobs, just to name a few. So today's class, we're going to be looking at Dynamo and Civil 3D, and we're going to be looking at how we can actually automate the process of creating and analyzing drainage cross culverts. So we're going to focus purely on pipe culverts in this exercise, but hopefully the learnings you can pick up from this, you can actually take and apply to all of your other types, such as box culverts and pretty much everything else. So split this up into 4 objectives. The first thing we're going to do is look at what we need to do from a Civil 3D side to actually prepare the model for import. And it is incredibly easy because Dynamo is going to do most of the heavy lifting for us. I should put a caveat on here. This is an intermediate to advanced course. The Dynamo graph is pretty big, but I'm going to try and explain it as best as I can along the way. In exercise 2, we're going to actually take the information from the Civil 3D model, we're going to slice it and dice it and actually generate geometry inside of Dynamo, and we're going to build out a culvert using user-defined parameters. We're going to step it up, then we're going to move into more automation, where we're actually going to start to look at leveraging the model to actually automatically size the culverts and determine the number of pipes we actually need to get the water from one side to the other. And finally, in Objective 4, we're just going to look at what we can do with that model. We're going to take the solid model from Dynamo, we're going to bring it back into Civil 3D as a solid object, and which we can then use in our downstream documentation. So I'm actually using culvert design guidelines. I'm using both North and South hemispheres in this case. I'm using the US DOT Federal Highway Administration guides in conjunction with the AusRoads, the Australian Guide to Road Design. Essentially, the guidelines are pretty similar. The workflows are actually identical. And you can see over here on the right, the workflow and process to actually design a culvert. How many drainage designers are in the room here? Okay, so great. So the first step, collect your design data. Okay, quite a long process. You need to get all of your road levels, your inverts, your ground levels, work out your heights. We need to determine and select a trial culvert, and we need to test it. And then we need to evaluate it, and then go back and select another trial culvert and test it. We're going to automate that whole process in Dynamo. Then we select our design discharge for the trials. We need to determine the inlet and the outlet control to determine the controlling headwater. We then need to look at things like culvert velocities for inlet and outlet control. And finally, we're just going to look at doing some basic design checks. This is not meant to replace your current design tools, such as programs like Hi8. However, you can actually just use it to get a really good first pass at your models. So from a Civil 3D perspective, all we're really going to be doing is leveraging the corridor. So all I've done in this case, I have a very simple corridor model. I have 2 lanes, some curbs. What I'm really focusing on, though, is we really just need to take note of our daylight strings, and I've called these IA, coming from an old program many years ago. And I have a hinge string here, which I'm just labeling EH. So what we're going to do is we're going to extract these strings from the Civil 3D model through Dynamo and extract the points along the top and at the base, and we're going to use those levels to actually determine our maximum pipe size. From a culvert setup standpoint, we need to consider 3 things, really. We're just looking for the chainage or the station. We need to know where along the alignment we're going to place this thing. We're going to look at we need the alignment string to reference it from, because we're going to be placing a Dynamo object at that point, and then we need to actually take into account any kind of skew that we want to put in. We want to make the culvert as flexible as possible, so you can just model these things up, literally in seconds, as opposed to how long it currently takes. And from the culvert and head wall itself, again, I could have put 1,000 parameters in here, keeping it pretty simple in this exercise. Most importantly, we're going to be looking at things like pipe size, the number of cells, the gap between the cells, and then we're going to look at, from the wing wall side, let's put in a few parameters around the wing wall thickness, the height of the culvert above the top of the pipes, the length of each wing wall itself we're going to individually control, as well as the angles. So we're going to set up a whole bunch of different parameters. We're just going to view them and see how we can set those up in Dynamo, make a few changes, and see how that affects our models. So just going back to the beginning, for those that are new to Dynamo, what is it? Okay, it's an open source software platform that's really designed around visual scripting. So you don't need a computer science degree to use Dynamo. You don't need any programming experience. You just need to have a basic understanding of computer logic. It's really good for geometry creation. It automates a lot of the tedious tasks that you do on a day-to-day basis. So if you don't have Dynamo, it was for Civil 3D, it is actually a separate installation. So you need to go to your accounts page, download the Dynamo for Civil 3D executable. Once you install it, it's located up on the Manage tab on the ribbon, over at the back here on the Visual Programming. Now there are two commands here. One is Dynamo itself. This will actually open up the Dynamo environment, which you can come in, play with your nodes, play with your wires, and basically go crazy. Run script are for those that aren't particularly confident to jumping into Dynamo. You can actually simply select this option over here, and it'll allow you to run a Dynamo script from the command line. So it's a very hands-off approach. Just a quick overview on nodes. Now the nodes are sort of like the cornerstone of Dynamo. Nodes basically are the building blocks of any graph that you create. So over here you have the 3 node types. Anything that has a green option with the plus symbol next to it, in programming terms, this is known as your constructor. This will actually create a new object for you inside Dynamo. In this case, we're looking at the point library here. I can create a point by coordinates. I pass in 3 values for the x, y, and the z. It creates a Dynamo point for me. The next are the actions or methods in programming speak. This is the red bar with the lightning bolt. This is going to perform an action on an existing object. For instance, a point, we're able to project it. I can take a point that sits at elevation 0 and I can project it onto a surface, for argument's sake. And lastly, we have the queries, which are our properties. A point, for instance, has 3 properties. It has an x, a y, and a z. And we need to look at extracting data from the model and drilling down and pulling that information out so we can start to leverage it in our design. In addition to the 3 node types, there are scripting nodes inside. You have your standard code blocks, which uses a language called design script. I'm going to touch briefly on that because it is the underlying language of Dynamo, and I'll just show you how easy it is to start learning the design script language. It is quite powerful. And lastly, my favorite, using Python. This is when you suddenly think it takes Dynamo and allows you to extend it in ways you probably never thought was possible. It's pretty cool. So just highlighting a few of the key nodes. You know, if you're relatively new to Dynamo and Civil 3D, these 2 nodes, which are located up here in your AutoCAD library under Document, we have the current document. This node here will extract the current AutoCAD document. This basically gets us underway. You're always going to need one of these. The document.model space, which is this one over here, when one is connected into the other, we extract from the current document the actual model space object block. Okay? That is what we need to send the data back from Dynamo into Civil 3D. The Civil 3D nodes, there are actually only 2 shelves in this. You have selection tools and objects. Now in the selection tools, at this point in time, there are only 4 distinct types of objects in Civil 3D that we can extract into Dynamo. Those are corridors, alignments, surfaces, and Kogo point groups. And you can see here, this little algorithm, I'm going to explain this in a little bit more detail here. This is just going to allow us to filter out and select just what we want out of the model. Okay? We don't want to bring everything across, otherwise we're just going to have too much information. And the Civil 3D objects, this is where we can actually start to extract more information about those corridors, for instance. This example we see here, we're taking from the left, we're bringing in and extracting the baseline of a corridor. Okay, and it's a natural flow. We extract the baseline, we're extracting feature lines from that specific baseline. So in this case, we're going to take the edge string and the ground string. But what we need to do here is we need to convert it and use a feature line and convert it to Dynamo geometry. So again, there's a lot of experimentation with this. There are a lot of nodes. It's quite new. But we just need to understand that workflow. Data from Civil 3D needs to be converted to Dynamo before we can actually perform the operations in Dynamo. And out of the box, Dynamo uses a lot of abstract geometry, things like coordinate systems. And if you think of a coordinate system as the old right-hand rule, you have your X, your Y, and your Z axis. From a civil perspective, these things are invaluable in that when you apply a coordinate system along an alignment or a profile or a baseline, it actually follows the direction of the line. So that allows us great flexibility in being able to calculate things like longitudinal grade, perpendicular change and offset, or anything that shoots out vertically from the roadway itself. A plane, in this instance, is a two-dimensional object that extends in all directions, and we can use planes in the Civil 3D Dynamo environment to actually go and create slices through the model. And that's what we're going to do when we lay the alignment string out. When we set out our culvert, we're going to create a slice in the ZX plane, and we're going to cut points through the model. And lastly, vectors. Again, vectors are basically a byproduct of all of our coordinate systems, X, Y, Z. Okay, so the first exercise, I'm going to go live. So we're going to look at actually opening up a manual graph, and we're going to step through it piece by piece and understand what's gone in behind the scenes. So it looks something like this. Trust me, that is not it's not a heavy graph. It does look bad, but we're going to break it down step by step. The key to understanding Dynamo is every single one of these nodes that you see would represent one line of code. So if you look at that, that's really not that big. But we're going to look at optimizing it in the next exercise. Okay. So we have a Civil 3D model here, and I'm just going to zoom into the area that I'm first focusing on. I want to create a culvert here. I could set this out. Again, I just drew a line here and thought this is where I want my culvert to be. You could use your flow lines out of Civil 3D, and there's some documentation on that that's provided as part of this class. But in the Dynamo sense, okay, so we've got our parameters here. We know that we want to skew this thing 15 degrees. I'm just going to head back to Dynamo and make it big. And I'm going to start over at the left-hand side here. These are my design inputs. Now, I've grouped all of my design inputs on one side of the graph, so it's really easy just to stay over here, just tweak it and see what we get at the end of the run. We have things like a number slider here, so I can set my skew to, I've set this between negative 45 and positive 45. That's probably a little extreme, and we can change the values there. I've used a code block here just to enter a manual chainage that we're going to use to extract off our baseline. We have a whole bunch of different sliders based around extending the culvert beyond the actual extent of the daylight slope, as well as adjusting the elevation. So I'm trying to give the user as much control as possible over fine-tuning the actual geometry of the culvert. Then we come down to looking at pipe sizes. Now, we don't want the users to be able to actually go and put in any pipe size. We want to actually limit them because they come in standard sizes. So in this case, we're setting up a list inside Dynamo of the standard pipe types, and we're hooking it up to a slider so that whenever I change the slider value, number 5 will be 0, 1, 2, 3, 4, 5. So we're going to use a 600 mil pipe with a 96 millimeter wall thickness. Okay? I can change this value, and it'll just correspond to the number in that list. Okay? Lists in Dynamo are 0-based, so the first element is index 0, just take 1 off. Then we have gaps between the cells, the number of cells, the skew upstream, the skew downstream. We're going to independently control the actual head wall skews at the same time, because once we skew the main culvert, those head walls need to rotate to be parallel to the roadway. And then we look at things like the wing wall angles and such. So once all those parameters are in place, a lot of these nodes don't get used until way down in the graph. Now, I could very simply take one of these outputs here and say, oh, I need to use this over here. Notice how it's going to create a very messy graph very quickly, okay? Dynamo is, again, a very visual tool. However, you need to be very mindful of how you pass data from one node to the next. So in this case, we're using what we call a pass-through node. Okay, so I'm going to take all these values and pass them up way above the top of the graph. This doesn't do anything. It's just containing the data and, again, just pushing it downstream. I like to think of these as cable ties for my code. Keeps it tidy. See, I'm just passing it along again, and then I'm using it down in here. And again, this looks really complex, but once you've set it up once, it's pretty straightforward. Okay, back to the start. If I run this graph as is, we always start from the left, work to the right. There's my document current. I'm going to retrieve the current document. I'm going to come down here and hit run. And it's going to take a few seconds to process all the nodes, but you'll notice immediately I'm getting errors because, quite simply, I haven't connected one up to the other. As soon as I do that, run it, you can see I've gone in, I've extracted information from the corridor. Now this node, this group here in particular, it's a pretty good algorithm. We extract the corridors from the model. Now I've only got one corridor here, but if I had 2, 3, 10 corridors, I'd need to just select the one I want to work with. So that's what this little group of nodes does. It says, okay, give me the name of this corridor, and then search for all of the names for this specific sequence of characters, in this case MC10. If it finds MC10, return true. If there was another culvert in there that didn't have that, it would return a false. These are called Boolean values, okay? A Boolean is simply a true or false. That's it. Then we use this handy little node here called filter by bool mask. So what it does is it's going to take a list of objects, which is over here, which is only one. It's going to take a list of Booleans that has to be of the same length, and it's going to split the list depending on whether they're true or whether they're false. Okay? This is a really good way to filter your information inside Dynamo. Then what happens is everything that's false goes to this output node, everything that's in goes to the input. Then we repeat the same process again. This time we've gone from a corridor into a baseline level. So we're now extracting the baseline from this model. And we're doing the same thing. We've extracted the baseline information. From here, we then extract the feature lines. Now, this is where you're going to start to see these sorts of warnings. If you see this, you may be tempted to actually take the advice and change the geometry working range. My advice is don't worry about it. We're going to come back. I'll explain that in the slideshow a bit later. So we get the alignment location, and then we pass in the chainage. We rotate. And then I'm temporarily using this block here to send the data back to the origin. Now, the reason I do this is because Dynamo does not like objects too far from 0, 0. Okay? It tends to fall over. Oh, not fall over, but it displays the geometry in a very jagged way, and it doesn't look very good. So by moving the data back to origin, I can work in Dynamo. It's close to origin. Everything looks the way it's meant to be. It's more of an interim step. And so once I've processed that information, if I select this node, notice it's actually highlighting in the background. Okay? That's going to be my set out point. Down here, you can see I've actually got my, let me just go in the background, zoom around a bit. I've got my daylight strings and I have my hinge strings. So now I've just taken a breakpoint here. Once I plug this element back in, that coordinate system, I'm going to create a vertical plane. I'm going to slice through the model. And that's what all this does. We create a ZX plane, we intersect the geometry, and then we simply adjust the verticals. So if I hit run now, okay, what we've got now is a slice plane down here. We've sliced through the model, and we've extracted the geometric points that we're going to use for the calculations of the culvert. And this is finally where we set up the actual culvert string. Now that culvert string is going to be used in a lot of locations downstream. Okay? That's the way Dynamo works. A node can only have one input, but its output can be used everywhere. And you can see here, when I select this particular element, that is, what is there, 1, 2, 3, maybe about 8 or 9 different uses of this downstream. If I want to actually replug a value from another node into this node, if you hold down the Shift key, use your left mouse button, you can actually drag all of the outputs from one node and reconnect it into another with a left click. Okay? So now we're going to actually essentially build the culvert. So if I hit run, okay, there it is. Okay, that was a little quick, but just let me explain what happened there. Okay, so essentially we're passing all of everything that we're doing to the right of that particular node is just building up geometry using vectors. Okay, it's grabbing the endpoints, it's extending objects out, and it's just using simple mathematics to do it. Now, see here, this particular group is actually just extracting the set out lines, the two-dimensional lines, and then we're passing it down into here to create the actual head wall geometry itself. Okay, and yeah, I don't have time to actually go through all of that, unfortunately. I'd probably need a day. But at the end of it, we end up with essentially a series of solids for the head wall and a separate set of solids for the pipes. Okay? And the benefit of this is we can now come back, and this is where, again, I like to color code, and it's good practice to color code all of your groups. I'm going to translate this data back to the world location. And again, the reason for that is I want to place this now back into my AutoCAD model. So my geometry is now translated, and this is the only node you need to push the data back to AutoCAD. So if I look at my model here at the moment, it's empty. Once I plug the geometry into that node, it's going to go on a layer called underscore head wall, and the block it's asking for the space, either paper space or model space. So you can see I've brought this up from here and saying, give me the document model space. We hit run, and you can see it's placed the culvert in there for me. Okay, it's pretty quick, it's really easy. The advantage of this is that once we've got this thing in place, we can now start to come back and make some tweaks. So if I come up here now and say, okay, I need that to be 15 degrees, type in 15, hit run, and it updates in both Civil 3D and in Dynamo. Okay? Just move this aside. The pipe size, we need to change that. Hey, no problem. Let's just rank this up to maybe 9. Let's take it up to a larger pipe. Again, run. And hey, why not? Let's just up the number of cells while we're here. So let's just move this across. Let's put in 3 cells. Again, just use a slider. I've set a maximum of 10. I think anything more than 10, you're really looking at a bridge. So there you go. So again, really simple workflows. The graph itself, it does look complex, but it's actually quite simple. But it does allow you, and this is sort of where Dynamo can really help automate this process. I mean, how long would that take someone to actually model up using standard AutoCAD processes? And then someone says, hey, I need 2 of them instead of 1. So yeah, again, this is a really good approach to automating your design. Okay, so a few things you might have noticed. Over on the left-hand side, we had the where we had all of our inputs in the pink graphs. It's good to use a template. Dynamo doesn't actually support a template out of the box, but to have something, a Dynamo graph set aside that you can just copy and paste, this is really good for adding things like information about the graph. You might not be the only one using it, so add some information to it to make it more readable for other people to use. So add things like the version, who wrote it, what are the known limitations, how do you use it, what are the external packages that are used in terms of dependencies. And you can put things like color coding there just to give people an idea, you know, group it, annotate it, okay? Because you'll come back to a graph in 6 months, hell, even a week later and think, what did I do? So always good to annotate your code and stick them in groups. So from a graph layout perspective, I mentioned before, inputs, best keep those on the left-hand side of your graph. They control everything downstream. Functions in the middle, all of your mathematical processes. Outputs on the right, okay? Really simple. Try not to back nodes, try not to back the wires on themselves if you can help it. I'm guilty of that in exercise 3, but sometimes it's unavoidable. So and I mentioned before the pass-through nodes. Again, Dynamo graphs can get very ugly very quickly. So you want to use that like cable tie method, so you can take something from that and make it look a little bit more like that. I mentioned before the geometry scaling issue. So you can see over here, this is a warning that's going to pop up. And it's good to know that, okay, it says here, your inputs lie outside the allowable modeling range, blah, 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 blah. If you're tempted to come up here to the settings, change your geometry scaling to deal with large coordinate systems, if you change it to large or extra large, it may actually change the way it calculates the geometry. So my advice on that is just ignore that particular warning, okay? The geometry's still calculating fine, it just looks funny in Dynamo. And that's what it looks like far from the origin, okay? So that's why those transform nodes is basically going to move the geometry from world space down to the origin. It makes it look a bit neater, so I can still work in it and actually see something. I don't know what's going on with that. That's what I like to work with. And make sure when you send it back to Civil 3D, if I send it back from origin, it's going to appear at the origin. So yeah, translate it back. Okay, manual culverts with design scripts. This is an exact replica of the previous exercise. What you're seeing here is actually the nodes of the previous graph with all the groups removed. And you can see there, it looks pretty ugly. Very difficult to read, very difficult to interpret. But what Dynamo allows you to do is use the underlying language of design script. Now, it's not a difficult language to learn because the commands are actually in each node. So what we can do is take all of this and make it look a little bit more like that, okay? It can be a little bit overbearing at first, I guess a little overwhelming, but there are certain circumstances where, you know, hey, a code block, it's good to use. It's just a simple mathematical function. Why do I need 50 nodes when I can put in maybe 5 or 6 lines of code? So in Dynamo, to learn this design script, the underlying language, there's a simple command, and it's really handy, called node to code. The idea is you select the nodes you want to convert, you right-click in an empty space on the canvas, I'll show it later, and you select node to code. However, what it does is it gives you this. It uses default out-of-the-box variable names. They don't really mean a lot. T7, T8, T9 means nothing. But what you can do is you can actually edit that, or you can begin from scratch, and you can make it look a little bit more readable. You can add things like comments, put some meaningful variable names in there, and then you can actually just keep it tidy, annotate it to your heart's content. So the question now comes, when do I use a node, or when do I use a code block? And I think that's really, there needs to be a bit of a balance. You could create an entire graph, send it all to a code block as code, and it would look horrible. No one could understand what's going on. But simple mathematical functions, things that you know are repeatable and work well, by all means, stick them in a code block. It works really well. For the more unique tasks that users must interact with more, probably stick with nodes. Again, it's best to understand who's going to be using the graph downstream. Okay, so we'll just go back a step. Let's have a look at design script. I'll just briefly go through this one, because you can see here, it actually looks exactly the same as the previous exercise. We have all of our design inputs, we have our cable ties or our pass-throughs, but note here, where we had all of that heavy geometry in the previous example, notice we've just replaced it with some simple code blocks, because I know the geometry in this particular instance, it's not going to change. The values I'm passing in are going to change the geometry, but the algorithm itself is going to stay the same. So in this instance, it was very handy for me just to convert it all into some design script code. Okay? Now, to convert it to code, if we come over here where we're actually creating the culvert setout string, I'm just going to hit run. And you can see we've already created the string here. Now these 3 nodes, I think, oh well, let's put them in a code block. So I'm going to select all 3 of those, right-click in an empty space, and select node to code. And you can see it immediately converts it to code. And you can see the sheer space it reduces. Some of the advantages of using code blocks is it actually can reduce your file size of Dynamo. Which, sorry? Oh, they're the outputs at each stage.
Each output
Correct. So that is, you can see it actually reduces space. It doesn't necessarily make the graph run faster, but it does make the Dynamo file smaller because it's not worrying about as many connections. So before I had about 3 or 4 wires in there. Now I've only got like the inputs coming in. So it is generally quicker. And then again, I'll take the output of that, plug that into my bottom output, which is my final resulting, hit run, and you can see there, I again have another culvert design. Okay. Just going to open up the next example in advance. These things can take a few seconds to load. All right, let's step it up a little. So we've looked at the manual process, we've looked at some design script. Design script is kind of like the intermediate language between nodes and the full-blown Python approach. But Python itself is a pretty easy language to learn. It's a legible scripting language. Does anyone here use Python? Excellent, yeah, it's pretty cool. It really does augment Dynamo in a way that, just makes it absolutely limitless in what it can do. It's an object-oriented language, and it is open source. Most importantly, it's named after my favorite comedians, Monty Python. It's built, the implementation of Python that's built into Dynamo is not pure Python per se. It is an implementation called IronPython, and it's a C# implementation written through the Microsoft .NET framework. And it uses the Common Language Runtime, or the CLR. Now, the Python node inside Dynamo, it's quite simple in theory. Oops, wrong way. Stuff goes in on the left, stuff gets processed in the middle, and stuff goes out the end. We can have as many inputs as we like over on this side here just by clicking the plus button, but we can only have one output. Okay? And that one output can be a list of items, so you can still output as much data as you need. You just need to handle it downstream a bit later. So the Dynamo Python node is located under the scripting options in the standard Dynamo library, under the editors with Python script. When you open up and add a Python script from Civil 3D, you get this. This is boilerplate code. Okay? It's a template to get you started. You don't need to use it. You can actually delete the whole thing and just start coding. However, there are a few lines up there you probably want to keep, maybe like import CLR. Otherwise, the thing probably won't work. But for the most part, all this is allowing us to do is access the Civil 3D API. So if you've got any C# experience, you can actually access the Civil 3D API using this sort of boilerplate code. This adds all of our references and gets us ready to go. We're not going to be using any Civil 3D API stuff for what we're about to jump into. We're just going to use standard Python. For those 3 reasons: for loops, while loops, if statements. Dynamo does have very limited functionality when it comes to creating conditionals. But because we need to go through the process and actually look at, hey, I need to compare this versus this. If this value is greater than that, do this. Dynamo doesn't do that really well. Python does. So what this enables us to do is build much more complex mathematics into our Dynamo graphs. So over here, what I'm doing is creating a couple of lists of pipe sizes. They were the same lists I used in the standard inputs. We then iterate through the range and say, okay, for the maximum height I have between my roadway and my ground, give me the maximum pipe size I can use, essentially. So that's really all we're doing. We're cycling through that list of pipes. We're calculating the actual maximum barrel height we're allowed to use based upon the geometry in the road. And then we're saying, once we get beyond that certain size, just give me the pipe size below it. That's really all we're doing. And you can see we've done this in less than, 50 lines of code? It's pretty light. And when it comes to calculating our headwater depth, this was the really tricky part. This is more of a goal-seeking function. We have 2 values that we need to evaluate in order to actually calculate the right value. So there's no known x value to iterate through. So we need to just keep iterating until we get those 2 levels that actually balance. So we use a while loop inside of Python to actually iterate over and keep changing the values until we get that within a certain tolerance. So this is the kind of example here. This does look a little bit heavy, but in a nutshell, what we're doing here is setting up a tolerance value here, okay? So when these two values get within a certain tolerance, we're checking these two values down here on lines 30 and 31, S1 and S2, okay? All this stuff up here is just calculating. This is standard engineering mathematics. It's just simple hydraulic calcs. Then we're comparing these two values, and then we're saying, okay, if one is greater than the other, drop that distance that we're trying to calculate by half, and then run the iteration again, and then iterate it by half of that again. So we're actually decreasing exponentially until we reach our goal, essentially. So really, up here, we're just saying, if that difference is less than the tolerance, yep, we've got our number, break out. I've also set another condition in here to say, do it until you hit a maximum number of iterations, okay? Because one thing you can do in a standard programming environment is if you set a while loop and you don't set a break condition, you need to exit the program, okay? And yeah, I did that quite a lot just doing this exercise. So essentially, oops, let me go back. So essentially, the way it works is, take the point at the midway of the pipe. Compare the two values. Do I need to go up or down? If so, go up by half. Then test those two values again. Do I need to go up or down again? Okay, go up by half again. Do I need to go up or down? And we just keep gradually getting less and less and less and less until we hit the sweet spot. That's my actual value that I'm going to use to drive my culvert design. And so with just a handful of lines of code, that whole process of selecting a trial culvert, testing it all out, doing it all manually, it's pretty much gone. So it's really fast. And finally, in this graph, we're going to set up a Boolean node down here. Now what this is going to allow us to do is say, okay, we've got the graph, we've calculated the pipe sizes we need, the number of pipes. Now let's let the user decide, do you want to use those values to model it, or do you just want to stick with the user-defined values? Okay? So a simple Boolean toggle in this case is saying, if that's set to false, just use the user-defined values. If it's set to true, let's actually use the stuff that we've calculated. Okay? And then lastly, we're going to take those values and push them all out to Excel. And we're going to make two sheets. The first one is going to be called the calculations. This is more for validation. Again, this is not meant to replace your high eights or any of those other off-the-shelf solutions, but it's just meant to give you an idea what we've actually calculated. And this is all done from Python, just using simple maths. And the last, we're going to export the culvert parameters, okay? Because in the next exercise, I don't want to have to model each culvert individually. We can record the settings from this graph, copy it into a master file, and I'm going to go and lay out maybe half a dozen culverts at once, based upon just some simple user parameters. So I'm just going to jump into the Python node here. And before I do this, I'm going to be overwriting this one, so I'm just going to quickly erase those solids. Jumped ahead a bit there. And okay, so you'll note that in addition to the standard design inputs that we have here at the moment, we also have now, because we're doing some calculations on the hydraulics, we actually have some drainage parameters. And again, I've kept this pretty simple for this exercise, but realistically, the sky's the limit on this stuff. You can go and build your own analysis tool if you wanted to in here. We've got some basic channel cross-sections. We've got our peak flows, some Mannings, and some freeboard values, as well as a maximum velocity. So I want to make sure that the outlet velocity is actually less than 2.5 cubic meters a second. And down underneath the design inputs, I've just said, simple Boolean, do I want to use the calculated values, true or false? Again, everything in this graph is the same, except for this. Not my proudest moment, but it does, as I could have put this all in one graph. I decided to split it up just to sort of illustrate each step along the way. So again, this is sort of based upon that flow chart I showed at the beginning, step-by-step account. Give me the allowable headwater. Calculate the tailwater, select the trial culvert, inlet, outlet controls, determine the controlling headwater. Oh, by the way, again, in addition to the graphs that are available on the AU website, I've also included in the documentation all the source code behind what I've written here. So feel free to tear it apart. Okay, so if we were to run this now, based upon those input parameters we had originally specified, actually I'll just hit F5 and run it. Again, this one does take a few seconds, but you can see it doesn't take that long. Here, where we're saying select the trial culvert, if I hover on my output there, you can see, again, this does look really complex, but really everything is sitting here inside the Python node. So I double-clicked on that to edit it, okay, and that's the code that's run. All this other stuff around it, that's a pass-through node, okay, so there's nothing happening there other than just storing geometry. These two code blocks here, that's just code, that's just comments. There's nothing serious in that. It's really, everything is just one node. I just did it so I knew what I was doing. So this has actually gone and calculated for me a 600 mil diameter with 4 pipes required to get under the road. Okay, and then we pass all that information downstream and do the proper analysis. So you can see here that is not a 600 mil diameter, and it is certainly not 4 pipes. Okay, and the reason for that is because I've set the toggle back to user controlled. So to fix that, let's go back and say, yes, I want to use the calculated values. Hit run again. Again, it takes a couple of seconds, but there's the update. So I now have my 4 pipes, 600 mil in diameter. Now, the great thing about this approach, using the automated design, let me just pan back to the Dynamo graphs, and you can see here it's still calculated those. So if I go back to Civil 3D, you can see it's actually still placing the model in the drawing. And by the way, this is actually a 3-dimensional model. Okay, so we can now cut cross sections through that if we need to. If I were to, again, just pop that back in there. If I were to take this alignment and, change it as happens, if I select a new profile here, just let this thing rebuild, okay? I don't have to do anything inside the graph anymore. The graph's done. Once the model changes, is that rebuilt yet? Yep. Okay, so I've just increased the road by about 0.5 meter. Okay, so remember before we had 600 mil diameter pipes, we had 4 of them to achieve the required peak flow value. Now I simply come back into Dynamo. Actually, I'll keep it on this. Hit run again. And it's going to, because we're actually using the model to calculate the extents, you can see we've now gone and resized. We've now got 1.05 meter diameter pipes, and we're now only using 2 of them. So it's completely automating that design process for us. In addition to actually generating the model, we're also taking all of this data. Notice the outputs here. I'm sending data down, obviously, to the next step, but I'm also taking it out, and if we track the blue line all the way up, don't be too intimidated by this. This is simply a pass-through node. All we're doing is taking all of those values, the parameters that the user is specifying, as well as the calculations. Okay? And then we're putting them into 2 separate lists. There's one list up here, which contains all the geometry parameters that we're going to use in the next exercise. This is the analysis part. So this gives me my Q per cell, allowable headwater, tailwater depths, and so on and so on. We then take these 2 across as code blocks. I simply create a header for this, because obviously when I spit this data out, I want to be able to know what it is when I push it out to Excel. Push that to the front so it sits at the top. Create a new list and use a data export Excel node, and it's going to pass it out to this file called Python export. Now, you didn't see it actually happen, but the minute I run that, Excel actually opens up with that particular file. And I can see here, that's just more for validation than anything else. So I can see here in this instance, I have my allowable headwater, tailwater depths. This is an outlet control culvert, and the outlet velocity is 1.3 cubic meters a second, which is fine. So I'm happy with that. I can now go and go and start documentation. In addition to that, we have the export culvert parameters. Now this, I haven't put a header on, but if I simply copy this line out, and again, we'll do this in the next exercise, we're going to actually build all of the culverts out at once. Okay, so I'm assuming that we're going to have 5, 10, 20 culverts along a reasonably long roadway. We're just going to build them all at once. Cool. Okay. Get there eventually. Okay, so multiple culverts from Excel. So the Python graph there actually took care of all the generating the parameters, automating the sizes, but now we're just going to bring it all together and actually just model a whole lot at once. So in this case, where in the last exercise we output our stuff to Excel, this time we're going to import geometry from Excel. We're going to rearrange the data using a very simple group of nodes there. And again, once you start getting familiar with the way the nodes operate, you can simply just copy and paste them from one job to the next. Okay? It's very, a lot of this stuff is very routine. Okay? And I'll explain what a lot of these nodes are doing as we go through, especially the imports. So, okay, let's jump back and let's go back and finish it off. Okay, again, I'm just going to delete these culverts because they are going to be recreated. So again, Control C, good old Lisp routines. Okay. So you can see in this particular project, I have 1, 2, I've probably got about 5 crossing locations here. I've just marked them in a big, thick blue line just to make it easier to see. So let's go back to Dynamo. I'm going to open up the last graph here. And again, each one of these was sort of built on the previous. That's why they kind of all look the same. Okay, so that's done. So in this instance, you can see here, everything is the same. We have our outputs over here on the right, inputs on the left, but the inputs here have been replaced now by an Excel file. So I'm just going to run this straight away. And reading Excel files is generally pretty quick. You can see I still have the geometry extracted in the background because that's running in a parallel process down here. It's still working. However, when I get to here, you'll see I'm starting to get errors. Okay, and that's because the data hasn't been fully completed yet. Okay. Now, what's happening here is we're actually pointing to a path, and this time we're pointing to the culvert setout file, which is this file here. This is, again, just something I built out from the previous exercise. Each row represents one culvert and its parameters. So you can see in column 1, you've got your chainage, your skew, your upstream, your downstream extensions. Again, I could have added another 20 or 30 columns on the back end of that, but I wanted to keep it simple. Most importantly, you've got the pipe size and the wall thickness. Again, once we read this data in, it's just going to interpret it and do exactly what we did in the first exercise. It's just going to model them all up at once. The only real changes we need to make to this file is instead of just passing in one item at a time to process the data, we're passing in a list of items. That's the only difference in this instance. So we've read the data in, and you can see it's given me a big list of elements, starting with the header, the chainages, the skews, and so on. This node here, called list.deconstruct, this is actually going to allow us to basically strip away the first line of an Excel file. Okay? That will go into this particular output here, called first. Anything from element 1 down goes into this list here. So it's kind of like stripping away the header in a nutshell. So we take the rest of the items, and because in this instance, you can see now in my rest list, these are my chainages. Sorry, these are actually all the parameters. So that's chainage, skew, offset upstream, offset downstream, etc. So each one of these lists represents a row. Now to process the data correctly, we need to transpose the list. We need to kind of flip it on its side. So instead of having however many here, 5 lists of 22 elements, or 6 lists of 22, transposing it essentially groups them all together. So now I have 22 lists of 6 elements each one representing one culvert. Okay, so this particular list here is the list of all the changes. This list here is a list of all the SKUs, and so on. So again, these two nodes in combination are ones that will be used frequently when you're bringing data in from the Excel file. If we pass that list into the placeholder here, again, this is a pass-through node. All we're doing is extracting each item from the list using the open bracket notation. So A is the input, 0 is the 0th element of the list. So essentially, all this data in here goes into this output. And then I can take that data from the output and use that downstream. So we hit run. And that was a bit quicker than I thought. You can see, again, everything in this graph is the same as what we've previously done. We just replaced the inputs from having one input to having a whole lot of them. And so I can add additional rows into that Excel file. Again, if we look at this, I threw a few together. I don't think you'd ever have a real world situation like this. But if I was to say, grab my third culvert here, come into the setout file and say, okay, that's changed 245. I need to shift that up the road 5 meters, make that 250. I want to change the SKU from maybe 7 to maybe, I don't know, -7. Let's have a look. Let's change the number of cells. Let's take that from 3 cells over here. Let's be really silly and make it 6, just to show what happens. As soon as you save your work and come back and hit rerun again, it's going to go through and recalculate that for us. So not only is it actually automating the design of it, is it still going? Yep. It's actually allowing us to store the information for that in a remote location that we can then use later on. There you go. Yeah, that's probably not my best culvert, but you get the idea. Now, at the same time, if I pass this along, I should have been pushing this out to AutoCAD. So you can see now I should have, oops, does that not come out? Okay, oh yeah. If you don't see it in AutoCAD, always go back to where you create the stuff and just make sure you plug that in there. Hit run. That's done. And so there's the models. Okay. Now, if I want to say use these in a long section, typically we just select the objects. This is real basic Civil 3D. Home, profile view, project objects, and I can then say project that on there. And I can annotate them and just display them properly. So again, just gives you some good work on your sections. In addition to that, we go back to the presentation. So you can see there, we can take the culverts and inside of Civil 3D, cut sections through them, long sections, cross sections. We can annotate them, put them in plan. In addition to that, we can actually also export these files to SATs from within Dynamo. So if you want to take it into Revit, for argument's sake, and you maybe want to do some structural rebar detailing on this thing, there's nothing to stop you. So take that pipe, export it to an SAT, bring the SAT file into Revit, put it in as project base point, and I've documented a process in the AU website that sort of details that process a little bit more. If you really want to get up to speed with Dynamo, there's a lot of good resources out there. The top two up there, dynamobim.org and the Dynamo Primer, are really good websites to get you going. You've also got things like blogs, there's YouTube videos, a lot of AU lessons, particularly this year, as well as your standard things on LinkedIn Learning, CAD Learning, Pluralsight, and the such. So with that, I'd like to thank everyone for their attendance today. I hope you've had a great time here at AU. I hope you learned or picked something up out of this. So thank you very much.